this will be recorded. Thank you.
Thank you very much, Dan, Nora, and hello everybody, and thank you for joining us. Take you through the slides in a couple of seconds. I will be speaking about Vallourec, who we are, what do we do, and then I'll be giving a little bit of information about the CCUS in Australia, and then we'll move to the risks and knowledge gaps that exist within the value chain, especially in the infrastructure development or CCUS. So maybe a little bit of introduction about who we are. Vallourec is a global leader of smart tubular solutions, where we provide products and services from standard to premium to energy industry primarily, but also other environments that demand um, technologies and solutions to address very challenging environments. As you can see on the map, Vallourec has a balanced presence in all around the world. We are present and doing activities in about 50 countries with almost 80,000 employees and about 4.2 billion euros of revenues in 2019. This balanced presence that I mentioned in the main four regions for Vallourec provides us with the global reach as well as the local presence that could help us to support locally our customers where they need us. A little bit about what segments and activities we are involved in. So obviously the energy industry and oil and gas, both upstream and downstream, are the main focus of the company. We provide premium tubular solutions and connections, what we call OCTG. So maybe keep this keyword in mind. So this is oil and gas, this is oil country tubular goods, the casing and tubing that we use within the production wells, as well as pipes for the pipelines for transportation of the fluids. And in the downstream sector, we provide tubular solutions for the refineries, petrochemicals, gas processing, etc. Another industry that we are active in is the industrial applications, where we provide seamless hollow sections, tubes, and hollow bores for applications such as mechanical engineering, automotive, and construction industries. So here it's mostly about the mechanical properties of our solutions, which stands out. And last but not least, the group has been active for decades in power generation industry, the conventional power plants and nuclear power plants. But the group has decided recently to divest its activities and in its place focus on energy transition and low carbon solutions. With that, I entered the energy transition organization of Vallourec. Within the group, we have 5 solutions, low carbon solutions. Here you see 4 of them because these 4 are included within the energy transition organization. The other one being solar photovoltaic is in another department. So I will focus on these 4. We provide tubular solutions for geothermal activities, offshore wind, hydrogen, as well as carbon capture, utilization, and storage. Maybe just to introduce the CCUS cluster within Vallourec, I will play you a very short video. This way, it's a good introduction, so we can go further after.
Ali, there is no sound on the video.
Sorry?
There is no sound. Sound is off.
Sound is off. Okay. I think there should be. Okay. Yeah, I think I know what is the issue. Sorry, I have to cut and then share again the slide. And there we go. Sorry for that. I forgot to include the sound of the computer.
cell, offshore wind, and storage, CCUS. CCUS is essential to reach net zero emissions. It consists in capturing CO2 at industrial facilities, which is then compressed and transported to storage sites deep underground. Vallourec's line pipes offer safe transport of CO2, and its line of OCTG products are adapted to safely inject CO2 underground. Vallourec also provides solutions to monitor the integrity of CCUS storage wells.
Okay, so yeah, this was a good introduction to the CCUS activities within Vallourec. Now I'd like to give a little bit of information about our track records and project references within the world of CCUS and CO2 related projects. We have in Vallourec plenty of knowledge and expertise when it comes to the CO2, and we have delivered solutions and supply projects when dealing with CO2 in the past and very recently. So as you can see on the top left of the slide, we have delivered to 2 projects for onshore CO2 transportation in Kazakhstan. We're dealing with some technical challenges such as very low temperature, coating, and a small outer diameter piping systems. We have also provided solutions for one very complex and very big project in Oman for onshore CO2 transport. As you can see, 125 kilometers of transportation of CO2, where the technical environment of the project required heavy vol products dealing with low temperature, as well as a very sour service environment due to H2S content. We have also delivered projects for offshore CO2 transportation in Brazil, what we call rises and flow lines for water alternated gas CO2 enhanced oil recovery. And also we have provided to 2 major energy companies in Brazil tubular solutions for more than 80 CO2 injection wells for multiple fields. For a portfolio of material, including from actually carbon steel to corrosion-resistant alloys and high collapse materials. So we do know what are the challenges, and we're familiar with the complexities of the projects dealing with CO2. Now, looking at Australia, and before entering the world of CCUS in Australia and moving forward, we have been active in Australia, and we have been known as a trusted partner for many companies in the energy sector in Australia. As you can see, we mentioned here a few examples with whom we have worked and supplied the products and services to them. So it's just an example of that we are also aware of the dynamics of the market in Australia. Australia and energy transition. So where does Australia stand to address the global challenge of reducing emissions globally? There are obviously 3 key elements today when we're talking about the reducing emissions. One is energy affordability. The other one is energy reliability in a world post-pandemic. This is I think these 3 are very important and key. And Australia has been trying to address these elements, prioritizing investment in emerging and low emission technologies. As you probably know, very recently the government has published a low emission technology statement where they clearly emphasize on 5 areas of activities: clean hydrogen, electricity storage, low emission steel, aluminum production, soil carbon sequestration, and finally CCUS. But why CCUS is so important in Australia and could have a lot of potential? So to talk about that, I used a set of data published by CERO, the research institute in Australia, which is very interesting and very much telling actually. So we see 3 segments with considerable export value and volume: coking coal, thermal coal, natural gas. And the size of the bubble shows the CO2 emission per export type. We can see these activities, which are quite important for the economy as well. They have quite a big carbon footprint. And for them in the short, medium, and long term to remain viable, these emissions have to be addressed. And CCUS could play a significant role given that the proper policy is in place and the proper infrastructure in the long term could be developed. The decarbonization could be addressed and CCUS could play a significant role. Obviously, in Australia, there has been a lot of demonstration and pilot projects dealing with CO2. But here, in this slide, I'd like to just give an overview of the major commercial scale projects. We have the Gorgon CCS project developed and currently operational by Chevron to decarbonize the Gorgon LNG plant. We have the Mamba CCS project of Santos currently under development to decarbonize their gas processing facilities in the Cooper Basin. And we have the CCS flagship project, Southwest Hub by Department of Mines and Carbonet by Government of Victoria. So there is obviously the momentum building up. We're seeing more and more activities, and given with the recent announcement that the policy could also be more favorable, if we could have a proper development of infrastructure, either for transportation or for storage, Australia could have a significant potential. To enter the subject of how we can actually bring about this infrastructure and scale it up to make sure that we can reach the aim of decarbonization at scale, first we have to have a proper understanding of the CO2 value chain. CO2 value chain is quite extensive with different steps. I'm not going to go through all the details, but in a few words, we have source characterization. What are the priorities to be decarbonized? Then we have the CO2 carbon capture itself, separating the CO2 from the flue gas, and then we have the purification. To what extent it should be purified, then compressed to the dense phase, supercritical phase, and transported offshore, onshore via ship or pipeline to reach the storage facility. There are three key messages and takeaways that we should actually address here. One is that in this, let's say, diversified value chain with many stakeholders, the CO2 that comes out of the emission sources, it will have an impact on all the steps down the value chain. So we have to make sure that there is the proper and direct communication between all the players to be sure that we have the proper and the smooth development of the infrastructure in the long term. But currently, because of this huge scope of work, this communication does not exist properly. Another point that should be addressed is that this value chain is getting more and more complex over time. The initial CCS projects that we have seen in the last 10 years, for example, they were quite from one single source to one single sink. So there were this like coal power plants or natural gas facilities that were decarbonizing and sending CO2 to their storage or utilization. But now with the diverse set of sources from biomass, steel, waste incineration, cement facilities, the CO2 stream, or what we call CO2 product quality, is changing, and it brings complexity to the picture. And even if for the long-term decarbonization, we are talking about the cluster mindset, the fact that we want to decarbonize a set of industries altogether. So the CO2 quality from one source, such as biomass, is very different from the CO2 product quality from power plant, for example. And when you're developing an infrastructure, so you have a diversified source with different type of CO2, and then using a centralized infrastructure and centralized storage, this is a very complex picture. So, which brings us to the final conclusion here, is that are we able to distribute the costs and risks along the value chain, or we're going to ask the carbon capture sources, which are already burdened with a lot of costs, to do all the purification themselves, and then later on have a smooth development of infrastructure for the down part of the value chain. 50% of the cost is carbon capture. Only 15% of the cost is about the storage, and the remaining for transport. So it's going to be quite complicated to ask everyone to in the top part of the value chain to purify perfectly, so we could have an easier transport and storage. So that's why today we're actually discussing more about transport and storage, because in the past couple of years, there has been quite a lot of research and discussion around the carbon capture, the technology, the viability of the technology. And because the transport and storage is coming at the end, less attention has been paid to it. So we think that there are fair risks and knowledge gaps in these two segments, and we would like to bring attention to some of them. But what are the risk and knowledge gaps in transport of CO2? First of all, as I said, the source, it really matters. Are we talking about CO2 from biomass, power, cement, etc.? Because each of them have their own CO2 impurity signature. Do we have water content in the CO2 stream? What kind of impurities do we have? To what extent, to what level do we have these impurities? Because some of these impurities, such as, for example, NOx, SOx, oxygen, they do not exist in the oil and gas environment. And the oil and gas return of experience is very, very poor dealing with that. And they can do cross chemical reactions, creating sour or acid environments, bringing about corrosion and crack propagation, etc. These type of risks, challenging the transportation, safe transportation that we want to have. Another point is that CO2 phase diagram is very sensitive to impurities. So we transport CO2 in dense phase, supercritical. So it's very important to keep it in one phase flow within the transportation step. The impurities could bring the pressure drop within transportation, and that will cause a two-phase flow, which is not wanted. And obviously, a significant pressure drop could bring very, very low temperature environment, and that's another risk in CO2 transportation. And in the worst case scenario, this will just, could we make sure, please, that everybody's on mute, please? Thank you. So in the worst case scenario, we might actually have failures, leakage, or blowout. And by that, I'd like to bring your attention to the picture on the right, which is an aerial picture of a rupture test performed by DNVGL in the Space Atom site, where they actually blew out one piece of pipe deliberately, and you can see the cloud of CO2 that is impacting the whole environment around the site. So now imagine you're transporting CO2 close to a population center, a city, a port. To what extent it could damage the environment or bring a health hazard to people who are living there. And another point is that imagine this is offshore transportation of CO2 close to a port, for example. And this CO2 that is being licked, or let's say it blew out the pipe, when it comes up, it grows in volume, and it could create, in worst case scenarios, could create artificial waves damaging the shipping line. So we're talking about a very important risk here. And when dealing with the cluster mindset that I said, the diversity of CO2, it's very important to make sure that there is a conservative design of the transportation, dealing with all those CO2 impurities from different sites over time, to make sure that there is a safe transportation. Well, how do we try to address in Vallourec some of these risks? In Vallourec, we provide the seamless products for onshore and offshore piping systems for transportation, and the accessories associated with those pipes. We have a large portfolio of materials from carbon steel and corrosion-resistant alloy to deal with those corrosion risks through cladded pipes. And we do have a very comprehensive set of coatings for such as a thermal insulation coating for flow assurance. We have the internal, external anti-corrosion coatings. But on top of that, the key point is that we have a set of experts in material selection that could provide the recommendation what is the best set of materials to deal with your risks, low temperature or corrosion, with the element of cost in mind, that to bring the most optimum material selection for that environment. We also provide the advanced welding solutions through our affiliate Cerimax for onshore and offshore welding, as well as digital solutions for efficient welding or handling of the pipes in the transportation segment for CO2. Now, looking at the storage, what are the risks in the storage environment? First of all, we talked about that everything that happens in the value chain will impact the other steps down the value chain. So obviously that CO2 stream, and with the impurities that it has, with the risks that it has, it comes to the storage side. So we are dealing still with the same risks of corrosion, impurities, etc. But in the storage, we're adding some other variables, creating a more complex environment. So not only we are dealing with a CO2 stream, that does it have water or not? Does it have impurities such as H2S, NOx, SOx, and oxygen? We also have to look at what is the storage environment. Are we injecting into a saline aquifer saturated with water, or we're injecting in the depleted oil and gas reservoir? What is the reservoir condition itself? Does it have water itself, chloride, the pH situation, the acidity there? Because all this together could create, in presence of water, corrosion risks. But also in injection scenario, we have what we call shut-in, where we stop operation for some reasons, for variable reason actually. It could be long, it could be short. Where we have a pressure drop leading to low temperature environments from -10, sometimes to -30, and the worst case scenario in terms of blowout, it could go down to -60, -80 even. So -80 degrees or even -20 degrees is not an environment that you experience in the oil and gas environment. So storage, where we want to bring a lot of experience from oil and gas, has a very big risk, which doesn't exist in oil and gas itself, actually. So how are we going to make sure that we use a material that is that could perform and bring and have resiliency to low temperature, but also to absorb this thermal shock over 20 years of injection, for example? Low temperature going back to normal, low temperature going back to normal over 20 years. This is a very complex topic. Another point is making sure that CO2 does not leak. So we have to have connections, connecting those tubings together or casings together that are perfect, that have perfect sealability. And how do these connections perform under such low temperature? I should again emphasize on the fact that in the oil and gas industry, never the connections have been tested before for this environment, or there is no qualification procedure for qualifying a connection at low temperature. So this is a big risk that needs to be addressed. And obviously, in the worst case scenario, you're dealing with safety failure, leakage, blowout that brings significant legal and financial liabilities, because if you have to stop your operation, you're not decarbonizing, and if your stoppage is taking quite a time, you will be liable in front of the government. And again, what do we do in Vallourec to address some of these risks? We do provide, as you can see on the picture, the casing, tubing, and accessories for injection of CO2 underground. We do provide premium state-of-the-art VAM connections, the best-in-class VAM connections, which will guarantee sealability to avoid leakage. We have a comprehensive portfolio from carbon steel to corrosion-resistant alloys to deal with the corrosion risks. And again, we have a group of experts in Vallourec in our research facilities where we'll recommend the best materials for that specific environment, keeping it to address the risks, but again, keeping the cost in mind to make sure there is a optimum material selection in place. We have our van field services for the field operations, tubular management services for handling of the pipe, as well as the digital solution for such as Running Expert that provides, for example, the elements of digital twin for the operators. I should also mention that when I talk, for example, about the qualification of the connections and the fact that this is a big risk, today we are working with some of the biggest energy companies in the world to define protocols and test procedures to qualify the connections, Vallourec connections for CCUS. And the fact that the preliminary results are showing that our connections perform properly under very low temperatures and do not pose a risk to CCUS operations. This slide, I just like to give us some insights about when we say corrosion in a storage environment due to water, what does it mean and how it looks like. So the first picture on the left, it shows the CO2 injection. So we have a simplified scheme of an injection well. We have the tubing, we have the casing, which is cemented. So if you can see here, so this is the casing cemented. This is a tubing that you have the CO2 injected in dense phase to the formation. We have the packer here separating the reservoir from the topper parts. So during the injection phase, we don't have risk of corrosion. Risk of corrosion actually happens when you do the shut-in, short-term or long-term. Shut-in, so you do 20 years of injection, a couple of times during the year, you stop your operation for some reasons, and I don't go into the details. And then due to this pressure drop, because you're stopping the operation, you have a gas phase of CO2 on top part of your valve, and then you get a wet CO2 due to contact with water, formation water on the bottom hole. So the risk of corrosion happens if your CO2 itself has water, so what we call wet CO2. If your CO2 stream itself has water, the risk of corrosion happens here, as well as in the interface between the tubing and the casing with the formation. So during the long-term shut-in, obviously, because your pressure drop is continuing, so the water comes, the wet CO2 interface increases and comes around the packer. So your risk of corrosion, so the interface that is exposed to the risk of corrosion is significantly increases to the area below the packer fully for the tubing and the casing. But when you restart your injection process again, your CO2 dense phase CO2 comes and then pushes the water back, and you're back to the step one, and no more risk of corrosion. So what we have to keep in mind as a takeaway is that risk corrosion happens during the shut-in process, and obviously during the storage period when you're stopped totally and your CO2 gets in permanent contact with formation water. How do we do material selection? And when we talk about, we have expert teams in place to help the clients with the cost versus risk element in the material selection. So this is sort of a let's say decision tree. So you have the simplified well again, the casing, tubing below and above the packer, and then your set of a CO2 stream. So if your CO2 does not contain water, or if there is no water in the environment, so we don't have risk of corrosion. It's very negligible. We can use carbon steel for the casing and tubing. So that's a simple procedure. But the risk starts when you have presence of water, either saline aquifer or formation water. Here you have three different scenarios. If you do not have any impurities in your CO2 stream, or you only have H2S, so sour environment, this is so we can say classic oil and gas environment. So based on the temperature, chloride, acidity, or the partial pressure of the H2S, we will do. So as I said, this is a classic oil and gas environment, and there we have in Vallourec an extensive return of experience from our production wells. We have a lot of tests on materials and plenty of data to be able to do the perfect material selection for that environment. The knowledge gap starts where you get impurities in your CO2. And this is what separates the CCUS mainly from the oil and gas environment. So where you have SOx, NOx, and oxygen that do not exist in the oil and gas environment, which gives you that orange box, how to do the material selection for below the packer. And that is why we have to adapt the material selection rules to CCUS, and that is why a proper material selection is key and very important. And how in Vallourec we try to bridge this gap, this part, is through our R&D activities and collaborations with energy companies around the world. We do have a powerful R&D asset within Vallourec. We have 6 advanced research centers in Vallourec around the world, in Asia, in North America, South America, and of course in Europe, in France and Germany. We have more than 500 researchers and technicians looking at R&D activities. We have fruitful partnerships with the universities in Europe, in US, and in Brazil, which provides us with also additional set of expertise that helps us to focus on that CCUS knowledge gaps that I mentioned and to bridge those gaps and address the risks. In recent years, we had plenty on CCUS and CO2 environment. We looked at, for example, through one project with the French National Research Association, we looked at how metallic material degrades in CO2 storage wells. And we published a scientific paper on this topic. We also, in recent years, we have been involved in 2 joint industry programs with with Total, Equinor, Shell, and the research lab IFE in Norway, looking at guideline of material selection for CO2 storage well in presence of impurities. That box that I mentioned earlier, how to address that knowledge gap in presence of water impurities. And also, what is the safe operational window for CO2 transportation in cabinetry pipes with those energy companies. So we are working significantly inside Vallourec and with partners outside to address those risks. I'd like to give a concrete example of how we do material selection when I say risk versus cost and bring value to the customers. This is a case study that we have done for a project with a very major energy company in Middle East, where we were dealing with an offshore environment, very, very extreme sour well due to very high content of H2S. So what you can see on the graph, just explain simply, you see the project environment, the project characteristic is the yellow star. So in terms of the level of H2S and the temperature, and those colored lines are the materials that could be used in different environments. So obviously you can see that the project conditions would have normally required the operator to go for the material called G3. It's a nickel-based material, very expensive material, advanced one. But what we did in Vallourec was that, and our experts brought to the table, was that we proposed a set of test protocols for the corrosion to prove to the customer that they can go for a material that is less, let's say, less noble, less advanced than the G3, but will do the job and will not compromise the risks, but with a significant cost reduction. We did we defined the test protocol with the customer. We've done it, and we proved technically that the 28 chromium material of Vallourec will do the job properly. And we published actually a scientific paper, and presently also in the ADIPAC fair. And we not only qualified this material successfully, we provided 30% of cost saving for that operation. So now, just to have an idea, we're talking about material which costs around 30,000 or even more, 30,000 euros per ton. So you can imagine that 30% cost saving is significant when you're talking about multiple wells. Monitoring. I'd like to speak a little bit also about monitoring because it's a very, very important phase in the CO2 storage, especially after injection. Yes.
You can spend 5 more minutes. You've come
almost to the end. I think I've got 2 slides actually.
Sure.
Yeah. Great. Thanks. So the monitoring, the monitoring and the risks associated with monitoring. It's very important to anticipate and avoid leakage in the well during the process. Why is that? Because the CO2 should not be licked and then should not migrate to shallow formations where it could bring contamination to underground water, soil, or air, because you have fractures, you have faults that could, if you do not have a proper well design and you're not monitoring properly, could bring the migration and then contamination, obviously the hazards to the environment and health of people around that site. We have also the operational risk. The well integrity could be compromised and risk of corrosion to those parts of the well that are not supposed to be in exposure to CO2. And in the worst case scenario, you can have your operation stopped, which again will bring you to the contractual failure and financial penalties that you could face. We have therefore developed an innovative solution in Vallourec for monitoring of this operation called Intelligent Pipe. Intelligent Pipe is generally an application developed for the exploration and production segment within Vallourec, but we have been adapting it for the energy transition, and we believe that it could provide a lot of values, such as real-time monitoring of the entire wellbore, anticipating the abnormality to avoid failure, and therefore ensuring safe injection and storage. We can also characterize the well environment, such as, for example, just an example is capturing any geological movements or access to information and for formation beyond the casing. And obviously with years of data that it provides to you, you can, with this data pool, you can actually optimize your operation over time as well. So monitoring is key, and we have this very innovative solution in Vallourec to address the risks related to that. And with that, I'll like to conclude my presentation that CCUS in general is a very important topic, and there are a lot of risks when we talk about transportation and storage infrastructure. But in Vallourec, we do have the products that are resilient to CO2, and we have the services that are adapted to this environment. Material selection is, if not the most important topic in CCUS transport and storage, it is one of the most important elements to mitigate the risks. In Vallourec, we do have the good knowledge on the material selection for existing applications such as oil and gas production wells and transportations, but we are adapting this material selection approach to CO2 based on the impurities that brings the complexity. When it comes to the connections, we have a comprehensive production. We're working with oil and with energy companies right now to qualify those connections because we are involved in some projects for example, in Europe on CCUS, and we have the support experts to adapt these connections for CCUS, and plenty of collaborations right now with external companies and energy majors to make sure that we can qualify and bring about the right materials and the right connections for the infrastructure development at a scale. So with that, oh, it's perfect, 14 minutes exactly. We can go to the Q&A session.
Okay, thank you very much, Ali. There are a couple of questions. The first one with the extensive track record of CO2 EOR, enhanced oil recovery, mainly in the US, what are the main knowledge gaps in transport or storage of CO2? If you could elaborate.
Yeah, sure. This is actually an interesting point because we get this sometimes this myth that because there has been transportation of CO2 for decades in the US or other areas, so we're doing CO2 EOR for long, even for many years. Why do we say there's risk? First of all, CO2 EOR, enhanced oil recovery, does not contain those impurities that I mentioned. So mostly the CO2 was coming from the gas processing facilities or other sources that maybe contain H2S. They do deal with H2S, but they do not have that nitrogen dioxide or oxygen. That doesn't exist. So that risk of impurities that we're talking, it doesn't exist. Another point about CO2 EOR is that when, for example, when it comes to the injection, you are injecting into the reservoir and then you produce. So the CO2 is not in permanent contact with your material and your formation water, for example. We're talking about 20 years of injection in CCS and after 100 years of storage. So after the injection period, your CO2 is there for 100 years in contact with water and with other elements with your material. So the risk of corrosion is much, much more significant. And obviously, the low temperature environment that I mentioned, that doesn't exist in the oil and gas applications. It's a topic, a very complex topic for CCS. So these are the differences between the CO2 enhanced recovery and the geological storage of CO2 in CCS.
Thank you. There is another one. How do you see the role of existing pipelines or depleted oil and gas wells in CCUS infrastructure development?
Yeah, this is a very fair question. It's an important topic as well because as one of the we had recently a talk with one of the CCS operators, developers, and he mentioned that CCUS is a sort of a fancy waste management at the end of the day. You don't have that revenue to bring the economics that you want. So you have to make sure that the costs are limited as much as you can, the CapEx. So it's very important if you can use or reuse existing infrastructure. It's also important for the energy industry because they don't have to go through the decommissioning costs of that activity. But there are plenty of risks involved with reutilizing existing infrastructure. One being that imagine a pipeline, you want to repurpose it for CO2. You have to requalify three topics. So you have to address the requalification of the direction of the flow, because you were, for example, you have to having the flow in one direction. Now you have to have it on the other direction. You have to requalify it for the extension of life, and you have to requalify it for the type of fluid that it changes. So because you had natural gas before and you want to, for example, repurpose it for hydrogen or CO2, it's the same. Another point is the operational design that has to be checked. Is your pipeline, for example, or your well, the material that you've been using, is it compatible with the CO2 risks, corrosion, and even low temperature? The pressure of the running pressure that you have, is it compatible with your pipeline? For example, an important topic is that in Europe, for example, the pipelines were designed for 80 bar. Are you going to transfer your CO2 at 80 bar, or for example, like in the States, you prefer to do it at 250 bar to avoid the pressure loss and having more boosters? And finally is the topic of, for example, public awareness and public concerns. We have been actually talking last week with a developer, CCS developer, which is going to develop one of the biggest projects in Europe, and he told us that they are not going to use any existing facility because they believe it brings significant risks in the long term, and they are going everything onshore and offshore on infrastructure for greenfield. So Yeah, I mean, when it is possible to requalify, there is no standards for requalification today as well. So it has to be defined. How are we going to requalify the existing infrastructure as well? When it's possible, it's very good. It brings significant economies, but there are a lot of risks.
Thank you, Ali. The third and last question, please. Please explain what is the advantage to transport CO2 in a supercritical phase?
Yeah.
And the question comes in three parts. In what kind of typical temperature and pressure range is CO2 transported? Please answer these two ones, and if you have time, I'll take you to the third one.
Okay. So CO2 is transported supercritical because of so first I go on the temperature and pressure. So it depends on it's a phase diagram. So you have the temperature and pressure. Generally, we can say, for example, the temperature is around 40 degrees, 30 degrees, and the pressure could be around 70, 72 bars for the CO2 supercritical, or what we call dense phase. The advantage of transporting CO2 dense is that it keeps the positive characteristics of gas at the same time with the same characteristics of liquid. So meaning what, for example? Imagine when you want to, for example, inject CO2 in supercritical, it has the density of water, density of liquid CO2, but it has the movement characteristics of the gas. So it moves very easily and smoothly into the pipe, but with for example, the viscosity of the liquid. So it brings that advantage to the transport, which makes it much more easier, and also for injection to the CO2 plume to move within the rock of formation for storage.
Okay, thank you. Then this is the last question from the same person. What is the leak risk in CO2 transport? Can it be easily overcome? And please, if you need a little bit of help from our people in the research center, feel free to.
Yeah.
Use that.
So I do not know exactly who is there, but maybe Cécile, if you're on, maybe you could answer that, or if we have Florian in the team, they can also answer that. But if not, I could also give some comments on this.
Go ahead yourself, and if Florian is there and Cécile, they can comment.
Yeah,
please
they
go
can
ahead.
comment. Yeah. So the risk of leakage, obviously, as I said, the CO2 is transported. First thing, very important thing is that the leakage. So we're dealing with CO2, and we're doing all those capital expenditure to make sure that CO2 is not emitted in the atmosphere. So if in any part of your infrastructure, either transport or storage, you have leakage and your integrity is compromised, so you're not doing the decarbonization that you wanted, right? So this is actually also one of the differences between EOR. In CO2 EOR, the industry didn't really put that much of attention on the point of not letting the CO2 get out of the system. But in CCS, you have to make sure that this decarbonization element is there, because if you're leaking and if the leakage is considerable, it's a risk. For example, we know that they say for a storage, 1% is okay. If you are keeping that during the storage period, 99% is still in the safe storage system. The other point is the public. I mean, it's a very big topic, especially in Europe. For example, when you're dealing with onshore transportation, the public is significantly wary of, let's say, CO2 leakage. So it's very important to make sure that the transportation will not have any leakage. So on the technical side, because CO2 is transported in dense phase and supercritical, any depressurization brings complexity. Why? Because, for example, the leakage could mean loss of pressure on that area, and loss of pressure means two-phase flow. So your dense phase will turn to gas and dense phase, and you do not want to have that two-phase flow because it brings complexities for transportation. At the same time, depressurization, because of that phase diagram, will lead to temperature drop. So you will, and in considerable pressure drops, you can have very low temperature environment, and which could bring fragility to your material and compromising the pipe integrity on that special segment. But feel free, Cécile, Guillaume. I see Guillaume is also there. If you want to comment,
Ali, Florian speaking. I can add another comment is. And it's especially when you would like to use whole pipelines that could be used for another kind of fluid, you have to take care that finally the way the gas loses its pressure depends on the nature of the gas. And I know that it's really a key aspect to know how CO2 supercritical environment will decompresses, will change. The gas behavior is really important, and it depends on the gas composition. And in terms of fracture, what you have to consider also is the way your pipe would behave as function of the nature of the gas. And so when using whole pipeline, would have been designed for instance, methane transportation or other kind of fluid. It's not really direct that you can use it for CO2 in terms of fracture behavior.
Can we then have it there and stop the discussion because we are running out of time? Thank you very much, Ali. Thank you very much, Florian. Nora, it's over to you to close the session, please.
Thank you, Leila. Thank you, Ali, for the presentation. Thank you all for being with us today on this CCUS webinar. The last thing I will be asking you, if you have 1 minute, is to click on the link I'm just posting on the chat to give us a quick feedback on the webinar. And you have a free sale, so feel free if you have a remaining question or anything you want to share with us, or feel free to raise the question and we'll get back to you after this webinar. Thanks again, everyone, for joining, and I wish you all a pleasant evening or a pleasant day. Thank you.
Thank you very much. Bye-bye.
Bye, everyone.
Thank you.